Welcome, everyone. Today, we're diving into the fascinating world of construction of angles and triangles. This is the first slide, so I want to warmly welcome you all and introduce our topic with some enthusiasm. We'll explore how angles and triangles are constructed, understand key concepts, and see practical applications. Stay with me as we go through this interesting journey into geometric constructions. Let's get started. Let's move on to slide 2, where we'll explore the construction of some standard angles. Here, the focus is on understanding how to accurately construct common angles, which are fundamental in geometry. These constructions are essential because they help us build more complex shapes and solve various problems with precision. Next, we'll look at how to construct a triangle when we know its perimeter and two of its base angles. This method is particularly useful because it allows us to create triangles with specific measurements, which is often needed in real-world applications. Finally, we'll see how to construct a triangle when the base, the difference between the other two sides, and one base angle are given. This is a more advanced construction, but understanding it will deepen your grasp of triangle properties and how to manipulate them. Throughout this part of the presentation, keep in mind that these constructions are not just about drawing. They're about understanding the relationships between angles and sides. These skills form the foundation for many geometric proofs and problem-solving strategies. Let's talk about how to construct the bisector of a given angle. First, the goal here is to find a line that divides the angle into two equal parts. This is a fundamental concept in geometry because it helps us understand symmetry and division within shapes. To start, you'll need to identify the angle you want to bisect, which is formed by two rays sharing a common vertex. Once you have that, the key idea is to use a compass to create arcs that intersect the sides of the angle. These intersections will help us find points that are equidistant from the sides. The next step is to connect these points with a straight line, which will be the bisector. This line splits the original angle into two equal angles. Remember, the precision in constructing the arcs and connecting the points is crucial for an accurate bisector. This process not only sharpens your construction skills, but also deepens your understanding of angles and symmetry, which are central themes throughout this presentation. When we talk about bisecting an angle, we're referring to drawing a special kind of ray. This ray is placed inside the angle, starting right at the vertex, which is the point where the two sides of the angle meet. The key idea here is that this ray divides the original angle into two smaller angles that are exactly equal in size. So, the main concept to remember is that the angle bisector not only starts at the vertex, but also splits the angle into two equal parts, which is really useful in many geometric constructions and proofs. This idea ties into the larger theme of understanding how to divide and measure angles accurately, which is fundamental in geometry. Let's go through the steps of this construction. First, we join AR and extend it to any point X. The key here is that the ray ax we create will serve as the bisector of angle BAC. This is what we're aiming to achieve in this step. Next, we move to step 4. With center P and a radius longer than half of PQ, we draw an arc. This arc helps us establish a reference for our bisector, ensuring accuracy in our construction. Then, in step 2, using center Q and the same radius as in step 2, we draw another arc that intersects the previous arc at point R. This intersection is crucial because it helps us locate points that are equidistant from P and Q. Finally, in step 3, with center A and any convenient radius, we draw an arc that cuts sides OB and AC at points P and Q, respectively. These points are essential because they help us determine the angle bisector accurately. By following these steps carefully, we construct the bisector of angle BAC, which is fundamental in many geometric proofs and constructions. Remember, the key concept is using arcs and intersections to find points that help us divide the angle precisely. Let's take a closer look at measuring BAX and CAX. When we do this, you'll find that BAX equals CAX, which is a crucial verification step. This equality confirms that our measurements are consistent and accurate. Verifying these values helps ensure the precision of our setup, which is essential for successful treatment delivery. By confirming that BAX equals CAX, we're essentially validating that our system is correctly calibrated and functioning as expected. This step ties back to the overall theme of accuracy and quality control in our process. It's a simple yet powerful check that reinforces the reliability of our measurements and, ultimately, the safety and effectiveness of the treatment. So, as we see here, point 2 indicates that AR is actually the bisector of angle BAC. Now, the first point tells us that PAR is equal to QAR, and similarly, APR is equal to AQR. These equalities set the stage for applying the SSS congruence criterion. Next, by the SSS criterion, we can conclude that triangles APR and AQR are congruent because they share the side AR, which is common, and the other corresponding sides, PR and QR, are equal since they are arcs of equal radii, and similarly, AP and AQ are equal because they are radii of the same arc. This congruence is crucial because it helps us establish the equality of angles and sides in these triangles. To visualize this better, we join PR and QR. This method, by leveraging congruence and the properties of the radii and arcs, ultimately leads us to the conclusion that AR is the angle bisector of BAC, which is the key point we wanted to prove here. Let's take a look at how some standard angles are constructed. On this slide, we're focusing on the basic angles like 30, 45, 60, and 90 degrees. These angles are fundamental because they serve as building blocks for understanding more complex geometric concepts. When constructing these angles, we often start with simple tools like a compass and straightedge. For example, to construct a 90-degree angle, we draw a right angle, which is straightforward and foundational. For angles like 45 degrees, we bisect a 90-degree angle, which shows how we can divide angles into equal parts easily. Constructing a 30 or 60-degree angle involves creating equilateral triangles and then bisecting their angles, which highlights the beautiful relationships within triangles. These constructions are not just mathematical exercises, they also help us understand the properties of shapes and how angles relate to each other. Throughout this presentation, keep in mind that mastering these constructions reinforces our overall understanding of geometry, making more advanced concepts much easier to grasp. These standard angles are essential tools, and knowing how to construct them accurately is a key skill in geometry. Today, I will walk you through the steps to construct a 60-degree angle using just a ruler and a compass. First, we start with a straight line, which will serve as our baseline. Then, we select a point on this line to be the vertex of our angle. Using the compass, we draw an arc that intersects the line at a point we'll call A next. Without changing the compass width, we place the compass pointer on point A and draw an arc above the line. Then, we choose a point on this arc and mark it as B now. We set the compass to a wider width, more than half the distance between A and B, and draw an arc that intersects the first arc. The intersection point of these two arcs is critical. Finally, using the ruler, we draw a line from the vertex through this intersection point. This new line forms a 60-degree angle with the original line, completing the construction. Remember, the key idea here is that we're using basic geometric principles, arcs and intersecting points, to create precise angles without any measurements. Now let's move on to step IV. Here, we will use the center O and a convenient radius to draw an arc, which we'll label as PQ. This arc will intersect the ray OA at a point we'll call P. Remember, using the same radius ensures consistency in our construction. Next, in step II, we take P as the center and draw another arc with the same radius. This arc will cut the previous arc PQ at a point R. This step is crucial because R helps us establish the correct position for our construction. Finally, in step III, we draw the ray OA itself. This completes the basic setup, and now we have a clear geometric framework to proceed with further steps. Throughout this process, the key idea is to use arcs and points to accurately define angles and lines, which is fundamental in geometric constructions. This method allows us to produce precise and reliable results, connecting back to our overall theme of mastering geometric techniques. Now, as we see here, the angle AOB that we've obtained measures exactly 60 degrees. This is a key result because it confirms our earlier calculations and the geometric construction we performed. Recognizing that this angle is 60 degrees allows us to connect it to the properties of equilateral triangles and other related geometric figures we've discussed. Remember, understanding these angles not only helps us solve this particular problem, but also reinforces the overall theme of how angles and their measures play a crucial role in geometric reasoning. So, this 60-degree measure is more than just a number. It's a fundamental piece that ties together the concepts we've been exploring. All right, let's take a closer look at this slide. We see that angle AOB is 60 degrees, which is quite significant here. Now, notice that OPR is an equilateral triangle. This means all three sides are equal, and all angles are 60 degrees as well. The angle POR is also 60 degrees, and since POR equals AOB, there's a clear relationship between these angles. Furthermore, in triangle OPR, we have that OP equals OR, and both are equal to PR, which again stems from the equilateral property. This equality of sides plays a crucial role in our reasoning. As we analyze this triangle, keep in mind that the equal sides and angles help us establish congruence and symmetry, which are key themes in our overall discussion of geometric constructions. It's these properties that allow us to make precise deductions about the angles and sides involved. So, in summary, this slide highlights the importance of equilateral triangles and equal angles in our geometric reasoning, tying back into how we approach and prove these kinds of relationships throughout the presentation. Now, let's take a look at some common constructions of triangles. These methods help us understand how to build triangles with specific properties or given conditions. For example, one key construction involves using a given side and an angle, which allows us to create triangles that meet particular criteria. Another essential concept is the use of known lengths and angles to determine the position of the third vertex, ensuring the triangle is accurately formed. These constructions are foundational because they connect geometric principles to practical problem-solving, reinforcing the overall theme of understanding how triangles are built and analyzed. By mastering these methods, we can solve a wide range of geometric problems more effectively. To construct a triangle, at least 3 parts need to be given. But not all combinations of 3 parts out of 6 are enough to actually build a triangle. For example, if you are given 2 sides and an angle that is not the included angle, then it's not possible to construct that triangle. This highlights the importance of knowing which parts to give and how they relate to each other when working with triangles. It's a key concept that helps us understand what information is sufficient and what isn't when we're trying to solve or draw triangles. To construct an equilateral triangle when the length of its side is given, we follow a series of clear steps. First, we start by drawing a straight line segment that represents the side of the triangle. This segment will be our base. Next, we find the midpoint of this segment, which helps us locate the center point for the next steps. From this midpoint, we use a compass set to the length of the side to draw arcs above the line, with each arc centered at the endpoints of the segment. These arcs will intersect at a point above the line, which will be the third vertex of our equilateral triangle. Finally, we connect this vertex to each endpoint of the base segment, completing the triangle. The key idea here is that all 3 sides are equal, and by using the compass and arcs, we ensure that the triangle is perfectly equilateral. This process is a fundamental geometric construction that highlights the importance of precise measurements and the use of basic tools like the compass and straightedge. It's a great example of how simple steps can lead to the creation of a perfect geometric figure. Let's start by joining points A and C to help us find the required triangle. This step is fundamental because it sets the foundation for our construction. Next, in step IV, we focus on the circles centered at A, using A as the center and the length of one side of the triangle as the radius. We draw an arc labeled by. This arc will intersect a ray we're about to draw at point B, which is crucial for defining the triangle's structure. Then, in step II, we repeat a similar process from point B with B as the center and the same radius. We draw another arc that intersects the previous arc by at point C. This intersection point C will help us complete our triangle. Moving on to step III, we draw a ray starting at point A, designated as ax. This ray will serve as one side of the triangle, guiding us in locating the other points precisely. Finally, in step I, we outline the sequence, emphasizing how each step builds upon the previous one. By joining these points and drawing the arcs with consistent radii, we're effectively constructing the triangle with the required properties. This method highlights the importance of using circles and intersection points to achieve accurate geometric constructions, which are essential for understanding the overall theme of geometric precision and reasoning. All right, so in this step, we're looking at how to construct a triangle when we're given specific information: the base, the sum of the other two sides, and one of the base angles. First, it's important to understand that these given elements are enough to uniquely determine the triangle's shape and size. We start by drawing the base, which is our reference line. Then, using the given base angle, we can locate the position of the vertex that forms the angle with the base. Next, since we know the sum of the other two sides, we can use that to determine how far along the sides we need to mark points, ensuring that the lengths add up correctly. This process involves a combination of geometric constructions and algebraic reasoning, but the key idea is to use the given data to methodically build the triangle step by step. This approach highlights an essential concept in triangle construction: how specific elements dictate the entire shape, and how understanding these relationships helps us accurately draw the triangle. It's a practical method that connects directly to the broader theme of geometric problem solving. Let's begin by drawing the perpendicular bisector of BD, ensuring it intersects with AD at point C. This step helps us establish a key reference point for our construction. Next, from ray ax, we will cut off a line segment AD that is equal to I, which represents the sum of the other two sides, BC and CA. This is crucial because it sets the length we need for our triangle. Then, we'll draw the base ob, which serves as the foundation for our triangle. After that, we join BC to form the required triangle ABC, connecting the points to complete the shape. Moving on, we join BD to reinforce the structure of the triangle. Next, we'll draw BAX, making sure its measure matches that of A, which helps us maintain the correct angles. Lastly, we obtain the base angle at A, and the sum of the other two sides, BC and CA, which we've labeled as I remember. OB is our base, O is the base angle, and I is the combined length of the sides BC and CA. This step-by-step process guides us through constructing the triangle with the specified properties, tying everything back to our overall goal of understanding triangle construction principles. Let's take a closer look at the relationship between AD, AC, and CB. We see that AD is equal to the sum of AC and CB. Now, if we want to find AC, we can rearrange this equation to say that AC equals AD minus CB. Notice that in the diagram, CD is equal to CB, which allows us to substitute CB with CD in our equations. So, AC equals AD minus CB, which is the same as AD minus CD. Now, moving on to how we identify the specific triangle we need. Since point C lies on the perpendicular bisector of BD, this is a crucial detail. It means that point C is equidistant from B and D, which will help us establish the properties of the triangle and justify our steps. Understanding this geometric relationship is key to solving the problem, as it connects the positions of the points and the lengths involved. This is how we build the foundation for proving the required properties of the triangle in our overall proof. Let's explore how to construct a triangle when we know its base, the difference of the other two sides, and one base angle. First, Understanding these specific conditions helps us visualize the problem clearly. The key here is that we have the length of the base, which serves as our foundation, and we also know the difference between the other two sides, which adds a unique twist to the construction. Additionally, having one base angle gives us a fixed point of reference for the angles involved. By combining these pieces of information, we can determine the possible positions of the third vertex of the triangle. The process involves drawing the base first, then using the difference of the other sides to set constraints, and finally, applying the given angle to locate the exact point where the triangle's third vertex must lie. This method emphasizes how different known elements, sides and angles, interact to define a unique triangle, illustrating the interconnected nature of geometric constructions. Understanding this specific case enhances our overall grasp of triangle construction techniques, especially when dealing with complex conditions. Now let's look at the next step in our construction. We draw the perpendicular bisector of segment BD. This line will intersect either ax or ax, depending on the situation. At a point C, this step is crucial because it helps us establish a key reference point for our triangle. Moving on to step VI, we compare the lengths AC and BC. If AC is greater than BC, we cut off a segment AD from ray ax, where AD equals AC minus BC. Conversely, if AC is less than BC, we extend ax to a point X, on the opposite side of OB, and cut off a segment AD from there, where AD equals BC minus AC. This process allows us to equalize certain segments, which is vital for the accuracy of our construction. Next, in step IV, we draw the base OB, making sure it has the length specified in our problem. Then, in step II, we join points B and C to form the triangle ABC. This step is about establishing the main figure we're working with. Moving forward to step VII, we join BD, which is important for the internal structure of the triangle and for subsequent steps. In step V, we draw the angle backs, ensuring it measures exactly the same as A. This helps us replicate angles accurately, which is key in geometric constructions. Finally, in step III, we determine the base angle, and the difference between the other two sides, BC and CA. We define I as this difference, either AC minus BC if AC is larger, or BC minus AC if BC is larger. This difference I plays a significant role in the overall construction, as it guides us in adjusting the figure to meet the given conditions. All these steps together form a systematic approach to constructing the triangle with the desired properties. Remember, the key points are positioning the perpendicular bisector, comparing segment lengths, and accurately measuring angles and sides. These concepts are fundamental in ensuring our construction is precise and reliable. Now, let's look at the relationships between these segments. We have AD equal to AC minus CD, which is also equal to AC minus BC. Notice how we're expressing AD in terms of other segments. Similarly, CD is equal to CB. This equality is important because it helps us understand the positioning of these points. Now, to find the specific triangle we're interested in, we need to consider the fact that point C lies on the perpendicular bisector of segment DB. This is a key geometric property because it means C is equidistant from D and B. By establishing this, we're justifying why certain lengths are equal and how that leads us to the configuration of the triangle we want to analyze. Recognizing that C is on the perpendicular bisector allows us to draw conclusions about the symmetry and the equal segments involved. This step is crucial for constructing the required triangle accurately, and it connects directly to the overall goal of understanding the relationships within this geometric figure. Now, let's explore how to construct a triangle when we're given the perimeter and two base angles. This process is quite fascinating because it combines several key concepts in geometry. First, we start with the given perimeter. Remember, that's the total length around the triangle and the two base angles. These angles are crucial because they help us determine the shape and size of the triangle. The main idea here is to use these angles to find the third angle, of course, since the sum of angles in a triangle is always 180 degrees. Once we've established all three angles, we can use the perimeter to find the lengths of the sides. Essentially, we work backwards, using angles to find side ratios, and then scale those ratios to match the given perimeter. This construction highlights how interconnected angles and side lengths are in triangle geometry. It also demonstrates the power of combining different elements, angles, side ratios, and the perimeter, to accurately construct a specific triangle. Throughout this process, visualization and careful application of geometric principles are key to ensuring the construction is precise. Let's look at the final step to complete our construction. We start by joining points AB and AC to form our triangle ABC. This is essential because it gives us the actual triangle we're working with. Next, we move to step VI, where we draw the bisectors of angles Xt and Xi. The intersection point of these bisectors is marked as point A. This step is crucial because it helps us locate the correct position of a base on the angle bisectors, which are key in many geometric constructions. Now, in step IV, we draw a line segment XY, making sure its length equals the perimeter P of triangle ABC. This segment acts as a reference for our measurements and helps us keep the proportions right. In step II, we draw the perpendicular bisectors of segments AX and AY. These bisectors meet XY at points B and C, respectively. This step is fundamental because it allows us to find the midpoints and establish symmetry, which are important for accurate construction. Moving to step V, we construct segments YDX equal to B and XYE equal to see these segments help us set the correct lengths for the parts of the triangle, ensuring our construction reflects the actual dimensions. Finally, in step III, we determine the perimeter P of the triangle and the base angles. We consider ABC as our triangle with perimeter P centimeters and base BC. This step ties everything together, confirming our measurements and ensuring the accuracy of our construction. And that wraps up the step-by-step process, showing how each part builds on the previous to accurately construct triangle ABC based on the given parameters. Let's look at this step-by-step. We start with the relation ACB equals AYC plus YAC, which simplifies to 2AYC equals CYE equals. See, this tells us that in triangle AYC, the angles and segments are related in a way that helps us understand the symmetry involved. Moving on, in triangle AYC, we see that ABC equals AXB plus BAX, which simplifies to 2AXB equals BXD equals BXY equals B. This indicates that the segments and angles in this triangle are also proportional, reinforcing the symmetry and equalities we're establishing. Next, we observe that XY is equal to AB plus BC plus AC. But then, we adjust this to XY equals XB plus BC plus CY, which emphasizes that the segment XY can be broken down into parts involving XB and CY, connecting these segments more directly. Now, an important point is that angles AYC and YAC are equal, which tells us that triangle AYC is isosceles with YC equal to AC. This is a crucial step because it confirms the symmetry of the triangle and helps us identify equal segments. Similarly, we see that point C lies on the perpendicular bisector of segment AX. Since angles AXB and BAX are equal, it follows that XB equals AB. This symmetry explains why point B lies on the perpendicular bisector of AX, which is fundamental for our construction. Finally, for the justification of this construction, we observe that B lying on the perpendicular bisector of AX ensures the equalities we've discussed. It confirms that our geometric setup is consistent and that the points are positioned correctly to satisfy these conditions.